Hello, geometry students. We are doing notes for 6.4. This is our first regular notes for the chapter 6 because we did some vocabulary notes and we also did some constructions notes. This section of the chapter will have actual worksheets. And so we're still talking about parts inside triangles. This first theorem that I want to talk to you about is called the triangle mid-segment theorem. So I will read you the definition of what this is. It has to do with a mid-segment, which is another kind of segment inside a triangle. We've talked about altitudes, medians, and angle bisectors and side bisectors and all that. Now we're talking about a mid-segment. The segment containing the midpoints of two sides of a triangle is called the mid-segment, and it is parallel to the third side and half as long as that side. So, for example, if I draw a triangle here, and I want to draw the mid-segment, I would have to create the midpoint of one side, and then the midpoint of the other side, and connect those two. When I connect those 2 points, then I end up with the mid-segment, which will be parallel to the third side and also half the length of the third side. So if this third side is 10, for example, the mid-segment would be 5. Now, every triangle has 3 mid-segments, so we have one more vocabulary word here, and that is the mid-segment triangle. Mid-segment triangle. It's kind of like a triangle inside a triangle. So let's say, for example, here that we have a right triangle and we want to draw one of the mid-segments like we just did. So we can draw the midpoints of 2 of the sides and then connect those with a line. That will be one mid-segment. But we could also do the same down here below. Draw another line with another mid-segment, and then we could also do this mid-segment here. All 3 mid-segments will be parallel to the side that does not include their midpoints, the midpoints that join them. And this is kind of like a triangle inside a triangle, so we call it the mid-segment triangle. Now, I want to just do one large example with you for the notes on this. And so I'm only going to do one example because we're going to need to graph this and use a couple different formulas. So let's go ahead and take a look at triangle ABC, and we're going to graph it on the coordinate plane. And I'm going to graph the points at -3, 6. That will be point A. And then B is going to be at 3, -4. And then C is going to be at -3, -4. And then I'm going to connect each of these points to form a triangle. So it may be easier for you to do this assignment on graph paper if you have it. If not, just try to draw neatly with a ruler. I just drew one of my lines a little off, so I just corrected it by erasing and fixing it. So we're gonna just do several instructions related to this one triangle. The first set of instructions says to find the coordinates of the midpoints of each of the sides of the triangle. So let's find the midpoint of AC. Midpoint of AC. Now the midpoint formula is something that we talked about in chapter 1. So that formula should be familiar to you. Basically, when we were calculating the midpoint, we add up the x's and divide by 2, and then add up the y's and divide by 2. So for AC, I've got -3 plus -3 over 2, and then 6 minus 4 over 2. which becomes negative 6/2 and 2/2, or negative 3, 1. Let's see if visually that makes sense. If we go 3 to the left and 1 up and put a dot, it does look like that would be the midpoint of side AC. Now, let's go ahead and also do the midpoint for side BC. So the midpoint of side BC. Again, we want to add up the x's and divide by 2, and add up the y's and divide by 2. For the x's, we're going to have the same work that similar work to what we just did. We're going to have negative 3 plus 3/2, and then negative 4 plus negative 4/2, which is going to then simplify down to 0/2, comma, negative 8/2, or 0, comma, and then negative 4. Let's place that on our picture as well. So that would be that point there. We can, if we want, call the midpoint of segment ACF, and we can call the midpoint of segment BCE. Now we just have one more midpoint to find so that we can draw the entire mid-segment triangle. In the interest of time, since we've already done the midpoint formula twice, I'm just going to tell you that that point ends up being 0, 1. 0, 1, this point right here. So if the instructions say to draw the mid-segment triangle, we would find the midpoint of each side, each of the 3 sides, label those on our graph, and then connect the dots, again, using the same formula 3 times. Now, the next set of instructions says to show that FD is parallel to CB. So show FD is parallel to CB. FD is parallel to CB. So FD would be this horizontal pink line right here, and we need to show that it is parallel to CB. So what we need to note is that the slope of FD is what? What is the slope of segment FD? It's a horizontal line, so the slope should be 0. And then the slope of CB is also going to be 0. So since the slopes are the same, the lines are parallel. So we've done that. Now let's compare FE and AB. FE, slope of FE, and then slope of AB. Since we already have a graph here, I think it would be easier to count. When we count out FE, we're going to go down 5 and over 3. So we can say negative 5/3. If we wanted to count out the slope from A to B, we would need to go down 10 and over 6, which at first looks like a different number. But if we reduce the numerator and denominator by dividing by 2, we can see that the slopes are actually both negative 5/3. So we've shown those 2 segments are parallel. And then the last 2 that we need to show are parallel is by comparing the slope of DE to the slope of AC. What would both of those slopes be? They're both vertical lines. The slopes of both of those lines are going to be undefined. So we know that those 2 segments are parallel as well because they have the same slope. Now, first thing that we've done, and this is really a great example actually because it illustrates everything that we did in our notes. We've constructed the mid-segment triangle by joining all 3 midpoints together. The segments, we've drawn segments between each of the 3 midpoints and formed a triangle that way. We've also shown that each of our mid-segments is parallel to the side that it is opposite. Now the next thing we need to show is we'll just pick one of the mid-segments. Let's show that mid-segment FE is half the length of mid-segment AB. So let's go ahead to do that and use the distance formula. This is a great review problem involving many of the formulas that we've looked at so far. So if we want to find the length between F and E, we can use the distance formula if we'd like. Or, you know what might be easier? Why don't I do one with the distance formula, and then I'll do another one just using Pythag. So F is at -3, 1, and E is at 0, -4. So I can label, if I want, x1, y1, and x2, y2. When I calculate the distance of FE, it's going to be -4 minus 1 squared plus 0 minus -3 squared, or the square root of -5 squared plus 3 squared, which is the square root of 25 plus 9, or the square root of 34. So that would be the length of segment FE. Now, let's go ahead and find the length of AB using Pythag. We know that if we want to find the distance from A to B, we can square the length of this side right here, which would be 10, and the length of this side right here, which would be 6. So to find the length of AB, we can use Pythag or distance formula again. So the length of AB squared is going to be 10 squared plus 6 squared, or the length of AB squared is 100 plus 36. We need to add the 100 plus 36 to get 136, and then take the square root of each side. So AB is going to be the square root of 136. Now let's take a look at the number 136. 2 is going to go into 136, I believe, 68 times. And then 2 goes into 68 34 times. So this is the same thing as the square root of 2 times 2 times 34. Who can remember how we simplify a radical? How do we simplify a radical? To simplify a radical, first we factor, which we already did, then we pull out pairs. When we do that in this case, we get 2 times the square root of 34. So the length of AB is 2 times the square root of 34, and the length of FE is just square root of 34. So now we have shown that FE is half of AB, because the measure of FAE is, because 34, square root of 34 is 1/2 of 2 times the square root of 34. This was an incredible example because we reviewed radicals, midpoint formula, distance formula, slope, and Pythag, as well as what the term mid-segment means, all in one example. So I hope this has been helpful. Thank you so much for listening. All right.